looking at section 4.5 on U sub. This will be day 2 of U sub. So hopefully you've watched day 1 or was in class on day 1 where we did basic U subs and trig U subs. So let's go into this notion of double substitution. Let's skip that. All right, so looking at problem 9, I'm trying to decide what I want to allow my U to be. I think it is a candidate for U sub, or at least I can't think of anything else to use at the moment because it's not a polynomial, so power rule would not work. And I see this multiplication between two functions there. So the only thing I can think of right now is to, let's get rid of that. The only thing I can think of is that we would use this inside piece to be our U sub. So we'll swing back into that and let's let U equal 2x minus 1. If I take the derivative, du dx is equal to 2, which means du is equal to 2 times dx if I bring it up and over. I can see a dx here that I could replace if I make this 1/2 du. So I've got this one taken care of, and this will be a u. And let's just pause a moment and rewrite then what we have so far. So I end up with u to the 1/2, this x, and then dx is going to get replaced with a 1/2 du. So there's a substitution made. For, whoops, 1/2 du, sorry, 1/2 du. Everything looks great until I look and see that I still have this x going on in my integral. Well, I cannot have a mixture of u's and x's. So now the dilemma is, how do I get rid of x? And if you think about it, go back over here where we had established u equals 2x minus 1, well, that gives me a relationship between u and x's. So I could take this and solve for x. Doing that, that's going to be a u plus 1 equals 2x, or a u plus 1 divided by x divided by 2 equals x. So let's replace one more time. This is why it gets the name of a double sub. Let's replace again that final x with a u plus 1 over 2, and then I have this 1/2 du. Well, I'm hoping you see what I see, and that is that I have a 1/2 u plus 1, 1/2 du. Get some parentheses there. This means 1/2, doesn't it? So I can take my 1/2, 1/2, call it a quarter, bring it out front since it's a multiplier. And that will leave me then, I'm just going to update here, that will leave me a u 1/2 times this u plus 1. So let's distribute and turn this into a polynomial. How did I get 3/2? I added 1 plus 1/2. I used exponent rules. When the bases are the same, you add your exponents. Now we can go into integration. And this integral will look like 1/4 of. Raise it by a power, so add a 1, divide by that power. But dividing by power is like multiplying by its reciprocal, so I'm going to write it as 2/5. Add with it u, pick up a power, so add 1, that's going to bring me to 3/2. Divide by 3/2, but that's like multiplying by 2/3. And then add my c, which you can do inside or outside of the parentheses. It won't matter. Now, another distributive step, let's take the quarter times that and the quarter times that. And that will lead us to 2/20 or 1/10 u to the 5/2 plus 2/12 or 1/6 u to the 3/2. Don't really need the parentheses like I put on the first one. I'll add them just so it looks the same. Final step is let's replace u with the x values that we started with. So I'm going to have to scroll back up, check out what was u originally. U was 2x minus 1, so 2x minus 1, 2x minus 1, replacing. And now we're back into x's, and that is the integral that we started. The integral is equal to this. Next one, we have 2x plus 1 and a square root. Well, typically for u sub, allow your eyes to be drawn to the more complicated part of your function, and I would say that is the 4 minus x. I know it doesn't look like it's going to sub out very well, but let's just kind of let things roll through, try something. If it doesn't work, we restart. So I know that this is equivalent to saying I have 2x plus 1, 4 minus x to the 1/2 dx. Okay, let's go over and do a little u sub. And my u will equal 4 minus x. Therefore, du dx, I'm going to multiply by dx, will give me a negative. This would be 0 for the 4, and then the derivative of negative x will be negative 1 dx. I just need to replace dx, so I'm going to call this a negative du equivalent to a dx. And I'm going to slide back over and update what progress I've made. I've got a 2x plus 1. And then instead of 4 minus x, that's what we said let be u. So that's a u to the 1/2. And then dx gets traded out for this negative du. I'm going to put my negative in front, my du for replacement of dx. All right, so now, kind of like last time, we have an x remaining, and we need to get that so it's in terms of u. So, back over here, what can we do with that? Well, let's take and solve for x like we did last time. So solve for x and see where that takes us. I'm going to add an x over and swing the u over, so it'll become add x and subtract a u, and it should give us x equals 4 minus u. And that can come back over and replace. So we'll get negative 2 times my x, which is 4 minus u. This will be a little bit more tricky, won't it? And then I've got a plus 1. Close that parenthesis because I just replaced 4x. U to the 1/2 stays as is, and then times the du. Now, looking at that, you're saying, well, this is not going to be easy to integrate, and I agree with you. So what we want to do is basically let's get in there and simplify, see if we can get it to appear like a polynomial. First simplification I'd do is take my 2 through. So I'm going to have negative 8 minus 2u plus 1. That is in the outer parentheses. Do you see those outer parentheses? We need to keep those intact. And then we've got this times a u to the 1/2 times a du. Okay, so I need to scroll, give myself some room, and keep simplifying. This is going to be a 9 minus 2u, still have parentheses, u to the 1/2 du. And now we've been dragging these parentheses along. Now let's finally approach the multiplication that needs to occur and multiply by that u to the 1/2. So I'm going to end up with 9u to the 1/2 minus 2u to the first plus a 1/2 gives me a 3/2 du. It is appropriate to have these larger parentheses times your du. It's easy to forget them. Now we're into simply integration, aren't we? So let's integrate this and see what we come up with for a final answer. So I have this negative out front, which I'm going to put in big brackets because that will have to be distributed at my last step. All right, 9u to the 1/2. U becomes power of 3/2 because we add 1 to it. We divide by 3/2. That's like multiplying by 2/3. Minus 2 u to the, let me give myself a little room, u to the 5/2, add that power, divide by 5/2, that's like multiplying by 2/5. And then we'll pick up our c because we're on an indefinite integral. Now it's just simplifying. 3 divided into 9 goes 3 times. So I have a 2 times 3 with the negative out front will give me -6 u to the 3/2. Minus minus gives me plus. 2 times 2 is 4, 4/5. U to the 5/2 plus 2, or plus c. I need to go find what u originally represented. I'm looking right here. It is 4 minus x, so it is final step of replacement, and it was 4 minus x, substituting back for our u, and we will have our answer. Now, these aren't as much fun to check your answer, but you certainly could by doing the derivative, and it should bring us back to what we originally had. Definite integrals, we're going to use the u substitution, probably back away from the double sub. I don't think this one's going to require a double sub, but what you're going to notice here different is that we now have bounds on this, right? So we have swung into what we call a definite integral versus an indefinite integral. So let's work on first just doing the u sub. There is a theorem, and I kind of glossed over it. It says if the function u equals g of x has a continuous derivative on the closed interval a to b, and if f is continuous on the closed interval, then this integral of f of g of x times g prime of x, so a composite function, is equal to f of u du with some different things going on for the boundaries. Notice they say it's going to be g of this a value and g of this b value. So we're going to update our bounds, and you're going to see how this rolls out. Let's let it go. So I want to bring this down just a little bit. There we go. So u sub. This appears to be my u. It's the inside function of the more complicated functions there. And if I took the derivative of u, if I take the derivative of something squared, of course I get something to the first power. So this looks like an ideal candidate to let it be, to allow it to be our sub. So x squared plus 1, walk through your derivative step. du dx, bring up my dx, is equal to the derivative of this right side, which would be just solely 2x. And I have an x dx, so let's divide by 2 and call this a 1/2 du is equivalent to an x times dx. Coming back over to my problem, I'm going to leave my bounds off purposely. You can put a box here if you want. We'll fill those in a minute. U to the third, x dx was a 1/2 du. So this could be written as a 1/2 integral. I still am missing my bounds because we were on a definite integral of u to the third du. Remember, I moved my half forward. Okay, what about these bounds? Well, I can change them to match the fact that I'm in u's. And if I change them, then I don't have to change back out of u's. So this is kind of a shortcut. It helps make this a little bit more manageable. How can I update 1 and 3? So when x is 1, I need to change it to u's. And when x is 3, I need to change it so that it reflects our rewriting our function in terms of u. Well, I have this u equals x squared plus 1, so I can very easily tell you what u is if I know x. We'll plug it in. So I put in 1, I get 1 squared plus 1 is equal to my u. which brings me to 2. So when x was 1, u becomes 2. So x was on the, or 1 was on the bottom. I'm going to update to a bounds of 2. When x is 3, u becomes 3 squared plus 1. Remember, we're putting it back into this relationship between u and x. So that calls for u being 10. So I'm going to update this upper bound to 10. Now that everything is written in terms of u, and all I need to do is the answer to a definite integral is a number, I can come out with that number here in terms of u and not have to change back to x's. So let's do our integration. And we'll have 1/2 u to the 4th divided by 4 and evaluated from 2 to 10. I don't need a plus c this time because remember we're on a definite integral. I could bring out the 4 and call this 1/8 and now evaluate u just from 2 to 10. And that would mean I'd have 1/8 times, this becomes the f of 10 minus f of 2. Like the theorem said, we can evaluate this f of u, we can integrate f of u with these new bounds. Okay, so this will turn out to be f of g of b minus f of g of a, if you want to think about it in that terms. Okay. Now we just got to plug in, don't we? So 10 goes in for u, it comes out as 10. Nice. 2 goes into my function, but my function's simply u, so 2 goes in and I get 2. And I get 1/8 of 8. Answer's 1. If you want to verify it, go back and throw this in your calculator and see what you get for an answer. Remember, you go into, you could do math and then find the integral, the function int, and put it in there. It actually is a little bit easier, isn't it? It's nice if I can stay in use because I created a much simpler function when I updated to use. This was my original function x's, and now in use, it's just really simple. U to the 4th over 4 was the integral. All right, let's try another one. A trig one. Well, we can work with trig on these as well. What should we allow our u to be? Well, remember how I typically said it's going to be the more complicated function. And also, if there's a denominator present, definitely look towards that denominator. So I think our initial try should be allow u to equal cosine of 2 theta. And don't worry about the cubing. We'll attack that when we come back and u sub it. It'll be u to the -3. So du will equal, derivative of cosine is negative sine of 2 theta. That was the outer function. Now take the chain rule and derivative of the inside would produce a 2. I'm going to put my 2 right here and then put a negative in front of it. Okay, looking at the top, this is a pretty close match, isn't it? Sine 2 theta, oops, I should have my d theta here, sorry. D theta, because this would have been a du d theta, wouldn't it? Our independent variable was theta. And then multiply up, we get d theta over on the right side. So back to what we were trying to do here. We wanted sine 2 theta, not -2, so we'll divide by a -2, which will make it a multiplication of -1/2. This will give me sine 2 theta d theta. All right, so we have our integration. So we could replace right now, and my replacement, I'm going to leave my bounds off, but I definitely got to come back and fill these in. Let's see, bottom. Cosine gets changed to a u cubed. Sine 2 theta d theta becomes a -1/2 du. Now, I'm going to make that a u to the -3 in a moment, but let's get our bounds straightened out. So we have this relationship, right, between u and theta. When theta was equal to 0, I'm going to deal with my bottom one first. When theta was equal to 0, you would become cosine of 2 times 0, which would make this 0. So I get cosine of 0. And the cosine of 0 is 1. All right, let's update our bounds. We get a 1 on the bottom because that's where the 0 originally came from. When theta is equal to pi over 6, you will become cosine of 2 times pi over 6. Well, okay, that'll make it the cosine of pi over 3. And the cosine of pi over 3 is, remember where it's located? Up on the top here. That would be a 1/2 value. Okay, makes a short distance over to the x. Tall, skinny triangle. All right, so we got a 1/2 there. Ooh, did you just notice something? Hopefully you noticed that we just kind of inverted our larger bound is now on the bottom, isn't it? And we learned earlier properties of integrals is if that larger number is on the bottom, we need to flip over our integral. And to do that, it takes a negative. So I'm going to have negative, negative to do that flipping and get my integration, my integral bounds switch back up. Let's write this as u to the -3 right now, du. So we can see definitely that this turns into a plus. And now we can simply integrate. So I have 1/2. The integral u to the -3, add 1, takes us to a -2, divide by -2. And then I evaluate this from 1/2 to 1. All right, let's pull this -1/2 out front, and I'll make a -1/4. And this becomes 1 over u squared because of the negative exponent. Okay. Okay, so rather than switching back to x's, we had already updated these. These were in terms of u, right? So we can just plug in. So I'm going to plug in 1. I get 1 over 1 squared, which is 1, minus 1 over 1/2 squared, which becomes 1/4. That makes this -1/4 of 1 minus 4, right? Dividing by a fraction is like multiplying by its reciprocal. So I get -1/4 times -3 produces positive 3/4. Just take a lot of care, you guys, when you're doing these. You know, you end up with negatives and negative exponents, things like that, that you just have to really watch for. All right, we are on 23 minutes and we're on our last problem. So let's get this done. Sketch the solution to the differential equation on the slope field. We've seen slope fields before. They represent the derivatives at any particular point on our coordinate plane. And it's the derivative of this original function. And then it says find the particular solution of the differential equation and graph the solution on your calculator and compare it. So we want to pass through this particular point. So let's just see what do we have going on here. Kind of goes up, shoots through there, kind of comes down, shoots through there. It's kind of a hard one to follow, isn't it? I'm kind of following this, and then it kind of directs me back. Yeah, kind of a goofy one. I'm not 100% sure on that, guys, either. So, all right, if we want to find the particular solution, here's the equation that gave us all these little hash marks, right? If I checked out a point, it would give me the slope at that point. We are going to integrate this dy dx. So I'm going to move my dx over to the other side. And I want to solve this, so I'm going to integrate both sides. Um, so this looks like a u sub to me. I notice that I've got this x squared and an x present. Well, the derivative of x squared is x, so let's set up our u to be x squared and do a little u sub here. The u dx, bring my dx over, is equal to a 2x. I simply have an x dx, so a 1/2 du is equal to an x dx, divided both sides by 2. Update this. The integral of dy will be y. Replacement here. X dx gets replaced with a 1/2 du, and the cosine will be of u, because the only thing I'm replacing is that x squared. Now let's integrate, so we get y is equal to 1/2. The integral of cosine is positive sine of u plus c. Now we have this going through 0, 1. But those would be x, y points, and I have yu or uy going on right now. So let's get ourselves back to x values, replacing, swinging back our u with our x squared. Okay, now we're going to find the particular solution. So we're looking for the equation that passes through, what was it, 0, 1. So where I have y, I put 1. Where I have x, I put 0. 0 squared is 0, plus some constant. The sign of 0 is 0, so I get 1 equals 1/2 times 0 plus c. Therefore, c turns out to be 1. And my solution is, remember how we come back to this particular point, and I can rewrite it now, update it with c. Update with c equals 1, and that's going to give me y equals 1/2 sine of x squared plus 1, replacing of c. Solution there. Okay, hope that kind of makes sense. Your homework is to complete this section, the page 305, and then Monday we'll come back to class and probably start with that problem. Okay, have a good day.